to Oleksiy Klurman from University of Bristol and Max Planck Institute for Mathematics. And Oleksiy is going to talk about monotone chains in multiplicative sets.
Right. Thank you. Sorry?
No, I'm telling Marco not to forget to record the...
Okay.
So I am in recording. That's fine.
Okay. Well, thank you very much for the opportunity to speak at this seminar. So what I want to talk about today is really a problem, very, very classical. In general, well, I'll keep it like quite a bit general. So if you really want details, I think there will be another talk sometime soon. So anyways, the problem that I want to discuss is a very classical one. So I've given you the sequence of real numbers and the shifts, H1, Hk. And if you take the random sequence in general, so what you expect really is that if you, to measure the randomness in this sequence, you can measure how many times each of the arrangements of these k integers occur. So if you believe in randomness,
Alexi, I think you're not seeing your slides.
You're not seeing my slides?
Yeah, only the first page.
Oh. Okay.
This is a common problem.
Yeah, me too.
I think you should set it full screen and then share it with us.
So before I think you were seeing, let me. What about now?
Yeah, now it's great.
Now it's okay. So try to make it full screen mode. Now you can see when I'm switching?
Yeah, excellent.
Yeah.
Okay, so let me then just repeat whatever I was talking about here. So I'm giving you the sequence of any real numbers, and I've given you the shifts, H1, Hk. And what I want to understand, if I give you the sequence, how many times each of the arrangements of these kind of arrangements occurs. So if you take a random sequence that any of the arrangements should occur with equal probability, and there is precisely a k factorial of these arrangements, well, you can ignore here, so I'm not putting that less or equal, because the probability of equality in random set is very small. But if you believe in the randomness phenomenon, then what you expect for the random sequence, or for the reasonable sequence, is the proportion is 1 over k factorial. And so really what I want to discuss today is how do you prove, how do you find such patterns in the sequences that are related to modular forms. So of course, once you actually study this kind of question, you very quickly realize that proving positive proportion of 1 over k factorial is a rather difficult problem. So even for quite a few cases, we would be good to settle with a modest goal of proving that each of these arrangements occur infinitely many times. So in general, I would like to talk about the sequences that are related to Fourier coefficient. I would like to understand this question when f is multiplicative function. So, okay, so the case k equals to 1 is, of course, obvious. So the first non-trivial case is k equals to 2. And for this, so let's try to understand a very specific example. So this is the function which counts the number of divisors. So this is divisor function. And suppose that for k equals to 2, I would like to show that each pattern dn bigger than dn plus 1 and dn smaller than dn plus 1 occurs with the often. If this is not the case, then we'll suppose that dn is smaller than dn plus 1 all the time, starting from some point. Then, well, this is very clearly impossible because you can just take n plus 1 to be a prime number. And then in this case, what you would have is that the number of divisors of p minus 1 should be smaller than 2. And this is, of course, impossible because you can, for instance, take p to be 1 mod 4 prime, and then these kind of numbers will have at least 3 prime factors. So it's very easy indeed to show that dn is bigger than dn plus 1 occurs infinitely often, and in the same way you can also show that the other inequalities occur infinitely often. So in this particular case, this problem is very easy for k equals to 2. I can't resist here to really show you. So what about the equality case? So the equality case, actually, if you ask the question of whether dn equals to dn plus 1, there was a beautiful work in the 80s by Claudia Spiro. So she actually showed that dn equals to dn plus 1 occurs on infinitely often, but not actually dn plus 1, but she had like 1 replaced with 5040, I guess. And Keith Brown actually got it to 1, and then Hildebrand improved the number of such occurrences, the density bound to x over log x to the cube. So this problem, this is a rather non-trivial, very beautiful result. But of course, going back to our question about monotonicity, so there is a general result of Erdős, which says from 50s, which says that basically that the only way that the multiplicative function is monotone, strictly monotone, is whenever f of n is n to the alpha. So notice here that I did not talk about our ambitious problem. This is only about infinitely many occurrences, but not the positive density results. And the reason why is that because the density version is quite a bit harder actually in general, and that has to do with the oscillating functions. So if the simplest example, I guess the classical example is the Liouville function. And the Liouville function, so this is -1 to the number of prime factors. And if we ask the same very question for the Liouville function, so we would say, ask like, how often is lambda n is smaller than lambda of n plus 1? So in this case, of course, well, you quickly realize that it's exactly the same question as asking when lambda n plus 1 has the sign pattern minus plus. Because simply, well, lambda of n can be plus 1 because there is nothing bigger. So it has to be minus 1. And it can be lambda of n plus 1 can be minus 1 because it would be equality. So this has to be exactly minus plus. So it's very easy to see that this sign pattern or this arrangement occurs infinitely often, simply because you can't have minus lambda all the time. But the question of whether this pattern occurs infinitely often, or sorry, positive density times, it's a content of the breakthrough of 2015 of Mathematica and Radziwiłł. So they actually showed that this sign pattern occurs, and any sign pattern actually occurs with positive density result. So this and much of the work, much of this progress towards understanding the sign patterns has been based really on this breakthrough. So what I want to do today is really to study the functions which are in the intersection of the two. So basically those are functions that grow, like divisor function, and the functions that oscillate, like Liouville. So I want to see what happens on the intersection of these two worlds. And the typical example of such things is the coefficients of modular forms. So for the purpose of this talk, I'll talk right now only about one very specific function to simplify the notations, but in general, the results will be valid for more general things. So this is the Ramanujan tau function, and the Ramanujan tau function is the this famous function that you take the formal power series here, and you expand it out this into the power series. And the coefficients of this power series are the tau function. And so this expression on the left defines the holomorphic modular form of weight 12 and level 1. But Ramanujan notice the very interesting properties of this function of tau of n. Well, first of all, the function is actually multiplicative, and so it fulfills the setup that I've been talking about. What you also notice that tau of p on the primes is actually bounded by p to the 11 halves, and Deline spectacularly proved it in the proofs of Weil conjectures and Ramanujan conjecture in this way. So this 11 is really 12 minus 1. So right now, as of last 10 years, we know even more. We know that if we normalize tau of p by p to the 11 halves, then we have a distribution function. And so this quantity is distributed according to the semicircle law. So that's been proved about 10 years ago by Planck, Hecke, Harris, and Taylor. So as you can see, this example is perfectly valid, perfectly appropriate for our goal, because you have this growth of the coefficients, and you also have the oscillating of the signs. So what is the conjecture? What would be the conjecture about our question when we rephrase it for tau? Well, in this case, we take the shifts 1 and k of distinct, and let me at the beginning assume the tau of aj is not 0. And the conjecture would be that the arrangement, when I restrict to the set of non-zero values, occurs infinitely often, or with positive density. So before I got the questions about these restrictions of why tau of n plus a is not 0, and so on and so forth, let me mention that there is a famous conjecture of Lemaire, which says that tau of n should not actually be equal to 0 at any point. And therefore, under Lemaire conjecture, you can actually get rid of these assumptions. And in this case, what you would expect is actually the density of these kind of arrangements should be also 1 over k factorial. But since we don't have, since we don't know the validity of Lemaire conjecture, we have to assume something to state the results. And the reason is that simply, well, you could deal with the zeros, but it's much cleaner in this way. So, and therefore, let me work with the sometime into one definition. So instead of working with all shifts, we're going to call the shifts a tau admissible if for any prime that divides the discriminant of these numbers and tau of p equals to 0, we have that there is a residue class such that these shifts are not congruent to 0 modulo p. So this is really a necessary definition, because if such thing doesn't exist, then we would just simply have that one of these guys would always be equal to 0. And this, that would be sort of not what we want. But in general, this is not that important. One can just keep in mind that if, say, A is the permutation, any permutation of the first 10 to the 23 numbers, then everything is admissible. And the reason is because it's numerically verified that tau of n does not vanish on these numbers and does not vanish on the primes that are small. So you can think, for the sake of this talk, that really those are some 100 first integers or something like that. Okay, so what is actually known about this conjecture in general, and used to be known? So the case k equals to 1 is really a statement. There is no inequalities there. So the k equals to 1 case is just that this is the statement of non-vanishing of tau. And on the fact that tau doesn't vanish on the positive proportion, it's actually a consequence of the result. It's a result of Serre from the beginning of 80s, I think. So the case k equals to 2, so as far as infinitely many is concerned, you can deduce it from results of Erdős or Rankin, but really the positive density, it seems that the first time the positive density has been obtained is a consequence of the result of Matamati residue. And the way how you obtain the positive density here for k equals to 2, well, essentially, you know that there is a positive proportion of sign changes. So if you think about tau of n plus 1, then you can make tau of n to be negative and tau of n plus 1 to be positive on the positive proportion. So that would be the consequence that this arrangement actually occurs positive proportion of time. Okay, and for k bigger than 3, it seemed to be that there is no known result even for infinitely many partners of this way. So the first theorem that I want to tell you about is I want to tell you a little bit about what happened, what one can actually prove. So let's take a tau admissible arrangement. So curly and shifts. So then what one can prove, and then this is the joint work with Sasha Mangerel. So for k equals to 2, one can prove that the upper density inside the set of where tau of n inside the admissible set is actually bigger or equal than 1/2. So this is the first result. Again, so as this improves on the previous work only in the sense of this quantity 1/2, which is before there was just a positive density result. So here, the interesting part that this 1/2, this is exactly the Sharp's threshold, because that has to be equal probability of occurring each of the inequalities. So the interesting part here is the Sharp threshold 1/2. So the genuinely new part, I guess, is the k equals to 3 case. And the k equals to 3 case, so before it seemed that there was not known the existence of infinitely many of such arrangement. But it turns out that actually what one can prove is that the upper density inside the set of non-vanishing is actually bigger than 1/6. So as soon as I show you that these sets, I would get a positive upper density results. And I guess one more note here is that really this is also 1/6 is really 1/3 factorial. This is also the Sharp proportionality constant. That's what we really expect. Okay, so this is the k equals to 2 and 3 case. So what can you say about k bigger than 4? So unfortunately, nothing unconditional at the moment, but conditionally on the Elliott conjecture that I will explain in soon, one can actually deduce the density result. And again, when I compare the density to the set of non-vanishing. So if you assume the limit conjecture, then of course all these sets at the denominators, those are just x. This is just the full set from 1 to x. So what one needs to remark is that this set should be actually big of curly mk, and this is the content of this proposition. So really, if you look at the set nk, then it does have a density, and for any k and any admissible tau admissible k tuple. So for k equals to 1, this is, as I mentioned, the result of non-vanish, and this is the result of SER, but it's not too difficult to prove that actually this is positive, that's got a positive density. I'd like to explain some of the ideas and what is the way to, in general, tackle theorems of this way, of this sort. Okay, so really, So the idea here is rather simple. So remember that our goal is to find the arrangements, find a lot of n's for which this arrangement occur. And really we believe in the randomness, so we believe in the densities 1/k factorial. So the first observation is that you can always write tau of n as the product of the order of magnitude times the sign. And if you were to prove the randomness in this vector, if you were to prove that this frequency of this arrangement, one way of doing that would be the following. So what you would want to prove, you would want to look at the vector of the magnitudes and the vector of signs separately. You would want to try to prove that there is a randomness, some kind of random behavior, joint independence in the vector of magnitude. You would want to prove the same kind of form in the vector of signs. And then you would want to prove some kind of disjointness. In this way, you would be able to compare it to some kind of random model. And that's precisely what's going to happen. So as a starting point, of course, if we forget about the signs, it would be interesting or natural to try to understand the same question when I put the absolute values inside. So instead of this arrangement problem, I would consider the problem with absolute values. And this is an interesting, this 2 years ago, this problem has been considered as approximation to the previous one. There is a beautiful paper by Bilou, Desolier, Gunn, and Luca, where they actually show that there is not a positive density result, so they lose powers of logs, but they do show that there is a lot of ends that satisfy these kind of equations, these kind of arrangements. And well, for our purposes, of course, if you want to compare it, like if you're aiming for any positive density result, you would need to get a positive density result, at least in this problem. That turns out to be possible. So one of the consequences, I guess, is that prove that prove that there is actually a positive density, and even the right density 1 over k factorial inside the set of non-vanishing. So nk of x, remember this is the set of non-vanishing of all the forms. So again, on the numeric conjecture, that would be just x. So that would be the first approximation, and we have to have this at least to be able to say something. So I'll pause right now here, and I will leave this order of magnitude question for a bit. And I want to talk a little bit about sign patterns. So as we mentioned before, I need to understand the sign patterns question as well. And the sign patterns question is really, okay, so in order to count just the sign patterns, so the sign vectors, say if I want to count the sign pattern minus, minus, plus, for instance, then the analytic way, the so this expression is non-zero only. So remember, I'm now ignoring the issue of zeros. So suppose that this tau, this sigma of tau doesn't vanish, So if I write down this expression, that this expression is non-zero only when I do have this arrangement minus, minus, plus. And if I open up these correlations, or if I open up these brackets, then what I get is like 1/8 of x, and then I get a sum of the 2-point correlation and 1 3-point correlation. So if I want to show that this vector behaves like random, which is each sign pattern occurs with probability 1/8, then I better show that these correlations are give negligible contribution. And so that very naturally leads us to the question of understanding the correlations of multiplicative functions. So we want to show that these guys give little of x contribution. And then we are led to the question of, okay, well, I'm giving you the multiplicative function, f, with the values of unit disk. And the question is, when is the correlation large? So if you believe in the philosophy that multiplicative structure of the integers is independent of the additive structure of integers, then you believe that almost all the time it should be little of x. So the natural obstruction to that is the periodicity. So if f is a Dirichlet character, then obviously there is a strong correlation between the values with the shifts. Slightly less obvious obstruction here is the function n to the it. And if you think a little bit about that, then the value of n to the it and n plus 1 to the it, those are actually two values that are not quite independent, because n to the it is very close to n plus 1 to the it. So in this way, there is a strong correlation between the shift and the function itself. But what we believe is actually that this is, in general, the only type of obstructions. So the general philosophy of this subject is that the correlations do cancel unless f is close to the twist of the characters. And this word close is really what we need to understand. So this is really what we need to understand in order to be able to handle our science of taus. And to quantify this word close, there is a conjecture of Elliott. So the conjecture of Elliott says the following. So if I give you G1, Gk, there's this, and I give you the shifts, then so long that there exists index J naught for which there is one function G which is far from any character and any n to the it in this way, then we can obtain the cancellation in the correlations, in the k-point correlations. And this expression here, this is really, so let me just try to explain it for people that haven't seen it before. So what that means is that, well, that means precisely that if this is not the case, then this limit would be, say, less than infinity, would be bounded. And that would mean that this expression is bounded often. And if this expression is bounded, that means that this product inside the real part should be close to 1 very often. On G should be very close to the function chi times p to the it. And this is precisely this manifestation of this general philosophy that I just mentioned on the previous slides. So this expression, actually, this is what this is a distance from G to twisted character in the language of Mangerel and Soundarajan. This is G does not pretend in the quantitative way to be P n to the it times chi. So, okay, so this is the conjecture of Elliott that was mentioned in the statement of the theorem. But what is known towards this conjecture is the following result. So this is the theorem of tau and Teravainen. So I'll state it for the three functions. And the theorem says the following. So it's, yeah, so it's like real life. We ask for more and get less, I guess. So by the asking more, so if I've given you three functions, G1, G2, G3, and I'm giving you the shifts, then to the product of G1, G2, G3, to any character is, well, it's not enough anymore to take the infinity, to request it to go to infinity uniformly, but you need a strong quantitative bound from below, so you request it to be bigger than log x. So the trivial bound, if you think about that, the trivial bound for this distance is twice log x. So you request it to be compatible to this order. Then one can prove, well, one can't prove really the cancellation of the correlations, but if you weight it by the weight 1 over n, logarithmic weight, then you can prove the cancellation. So it's a still very strong theorem, and for instance, it applies for the U-wheel function, and that is exactly what one would need to for our purposes. Okay, so right now what I want to do is I want to really get this cancellation, so we would need to show that our sine of tau, function of sine of the modular form, should satisfy the strong conditions, should be far from the twisted character in the uniform way. So what I want to do right now is I want to really explain a little bit more what is behind those theorems, really. And so I would need a little bit of terminology here, but you can think of that, of all these, if you wish, you can think that all these functions f1 of k are actually the modular forms corresponding to the function tau. Okay, so here is a little bit of words. So let f1 of k, those are Hecke cusp forms of weight n square free level. Again, you can think of that as being all equal, if you want, and all equal to the delta function. So beta of A, this is a product of intervals. Open intervals. So then each of these holomorphic forms, Fi, it has a Fourier expansion with the coefficients of Bj. So again, you can think of that if f is the Ramanujan, if f is the function that I stated before, then you can think of Bj as the analogs of tau. You can think that they're all tau. And so lambda j's, those are normalized Fourier coefficients. So I divide by these powers of n, and for tau it was n was 12, so that was exactly 11 halves. So these curly and j's, those are my sets of non-vanishing, and again, conjecture of Lemaire, you can think of them today, they don't vanish, at least for tau. So curly n, this is my common set of non-vanishing of all the Fourier coefficients. Again, as for tau, you can prove that this set density. Okay, so the non-trivial non-trivial notation here is that instead of studying the function lambda, which actually fluctuates very erratically at the size, it's more convenient to study logarithm of this function, of the absolute value of lambda. And in this way, the function becomes not multiplicative, but rather additive. And so I'll normalize it in this way, and I'll explain it later where it's coming from, but for people, of course, that are familiar with Erdős-Kac type theorems and with the central limit theorems, so this is really a normal order and standard deviation that comes up from the central limit theorem. So, and A1, AK, this is our, is this shift, which is F admissible. And F admissible is exactly analog of tau admissible, except that right now I take that n plus A1 n plus A2 corresponds to F2, and Fk corresponds to n plus Ak. So it's exactly the analog of this non-vanishing statements. Okay, so this is the setup to understand the order of magnitude of lambda, but we also need to understand the signs, as we discussed before. So here's a little bit more notations. So here the epsilon would be the k-dimensional sign, and sigma j would be also the sign. And the set that I'm interested in is the following set. So my shifts, I would like my forms, Fourier coefficients, to be non-vanishing on these shifts. And I would like to have a prescribed sign of tau on n plus Aj, so with the sign button turn j. And I would like the order of magnitude of this normalized order of magnitude to be in some certain interval. So it's precisely the problem that I want to understand, and I would like really, so we know that the set of the common set of non-vanishing, this is what I said before, the common set of non-vanishing is actually quite large. So it has a positive density, really. And one can establish that in the same way as generalizing this result of set. So really the theorem that is behind, okay, this is a bit heavy maybe about the notations, but really I'm interested prescribing the sign patterns and prescribing the order of magnitude of the coefficients. So behind this, the theorem that is really behind all this business is the following. So it's also joined, of course, with Sasha. So if we assume the Elliott conjecture, the first statement, if we assume the Elliott conjecture, then we understand the counting function of this set. And namely, this counting function is given by this joint Gaussian behavior. So this integral is a joint Gaussian behavior. And so this corresponds to the joint distribution of the order of magnitude of these forms. And this 1/2 to the k coefficient, that comes from the sign part, which manifests as a Bernoulli 1/2 random variables. And this product here exactly says what we described before. In this what we talked about about the strategy, it describes that they behave in a disjoint way. So this is conditional on the Elliott conjecture. So what one can say unconditionally is that for k equals 2 and 3, and here is a very important type that the two of the forms must be the same. So if you think about function tau, then there is no restriction here whatsoever. Then we look at the counting function, but now with the logarithmic weight, with the weight 1/n, as in the correlation problem. Then one can actually prove exactly the same type of statement. So you have the Gaussian type behavior and the Bernoulli 1/2 type behavior of the signs times this proportional constant of 1/n. Behavior. And I should notice here that there was a previous work of Florian, Max, and Igor, where they did not consider the signs. So they did not consider the signs. So they only considered the absolute values, and they considered the case k equals to 1. And so they proved this central limit theorem, or Ebers-Katz type theorem, this Gaussian behavior for this. They're conditionally on the error term in Sato-Tate conjecture, but that's now available. But anyway, so there was a previous work which has not treated signs, and the case k equals to 1. Okay, so what I want to do right now in the remaining time. Sorry?
Yeah, I think
there is a question? No, there is no question. Okay. So in the remaining time, I'd like to tell you a few words about how one proves this type of theorems very, very briefly, and maybe discuss something more. So very, very roughly, so let's take let's assume right now that we are working on rather not f1 tau, but everything. So this is not a good notation. Let's assume that we are working just with the form with the tau, and our lambda tau is this normalized tau function. So the way to prove these theorems, so we talked about the signs, but the way to treat the orders of magnitude is really the first step would be to approximate our function lambda tau by the products, by the truncated products. And what I mean by that is that I would want to get rid of two things. The first thing I would want to get rid of is the large prime factors. And And the second thing that I would want to get rid of in this, so if I want to approximate, remember we want to prime p, which divides integer n, for which lambda of p is very, very small, then logarithm is going to explode and going to be extremely big. So if I'm to prove some central limit theorem, then I would want to actually, then I would have some explosions if I want to compute the moments or something like that. So the first step would be to sieve out those integers n for which there is a prime for which lambda p is extremely small, so smaller than this quantity. And that brings us to the following a very important thing that became available. So if I would want to sieve out, if I want to look at this set of integers free of prime factors with small contribution here, I would need to know, so we do know the distribution of lambda tau, as we discussed before, that is a Sato-Tate distribution, but we would need to have a Sato those primes to go to 0 quantitatively while computing moments. So to make this, and therefore we need the Sato-Tate result with the error terms. And this is really what became available in the last year. So the James Newton and Jack Thorne in 2019, the end of 2019, they proved the automorphic, and they proved an analytic continuation for all symmetric powers of the L function associated with the new forms of square free level. So you can think of tau function here as well. And that was a big breakthrough, but it was known before that once you have this information, so there was a word before that you can actually deduce the Sato-Tate distribution theorem, the Sato-Tate result, with the explicit error terms. So this is, and there was a previous word. So I quoted here the result, very recent result of Jesse Turner, who gets, well, for tau function, he gets more the uniformity, but really for tau function, that would be that the number of primes inside the interval I is this constant which comes from the Sato-Tate distribution times the number of primes plus the error term. And it's important here that the error term, so well, the number of primes is x over log x. So this is here you save the square root of log x roughly on the error term. So there was word before of, I guess many people actually, Steve Miller and Jesse himself, and Jesse with Robert Lemke, known that you can deduce this. And okay, so one actually needs, for our purposes, I guess I'm not going to state what you really need, but because if you remember, we need to also show that the sign function of tau is far from any Dirichlet character times n to the it. So you need understanding of your function tau or sign tau inside the arithmetic progression as well. So you also would need some version of Sato-Tate for the arithmetic progressions, which you can actually deduce using the same methods. One can prove it. It's not difficult. But once we sieved out those bad primes, which give us bad, so from the previous lemma, so once you have this Sato-Tate, you can sieve out bad primes that give you a reasonably small contribution. You can also sieve out large primes, and you can only work on the. And then once you do that, what you can do is you can compute the moments. well, in practice, you need to disjoin this from science, but you can compute the moments, and using these ideas of Granville and Sound, where they prove like their Erdős-Cut, they have a paper on Erdős-Cut theorem. So you can use similar ideas to actually compute the joint moments. So here I'm again back to the setup where I have K forms. And so these are your additive right now functions. These are the expected values of these additive functions. And once you compute the moments, you can compare them with the Gaussians and get the conclusion that you want. So perhaps I could tell you a few words. Why exactly do you expect, just very roughly, why would you expect a Gaussian behavior? Well, so for the additive function, this is a very general. If you take a logarithm of the multiplicative function, if you get an additive function, then really what this product just simply becomes a sum. And so now if you believe in this fact that for the integer, the events that the integer, for two different primes, p and q, the events that p divides n and q divides n, okay, they're independent, then upon taking this logarithm, what you do is, if you believe in this random model, you have a sum of independent random variables weighted by something. Well, in this case, Sato-Tate distribution. So you have the sum of independent random variables, so you're in the position to apply the central limit theorem, and therefore you get a Gaussian as an output. So it's really, that is what is behind that. So it's actually true for many, many additive functions. And this joint Gaussian behavior is also a manifestation because the integer so you get this independence, strong independence. So I guess I'll conclude here. So once you compute the moments, or rather you can compare it to the Gaussian, once you can use these ideas on the correlations to handle the sign patterns, and you can patch them up together using some Fourier analysis and get those theorems. So let me just mention one very quickly. So the interesting, perhaps very briefly, that the interesting part is that these exponents 1/2, 1/6, and 1/k factorial, they're quite sharp. So these are exactly the lower densities that you expect. And so the reason why you get these densities, which you don't lose in them, is because of this covering arguments. And the covering arguments, so how do you deduce, after this central limit theorem, how do you deduce really the arrangement patterns? Well, you can start off with the intervals, I1, I2, Ik. So these are, by that inequalities, what I mean is that you stick one interval and then you take non-overlapping interval such that the both left and right end are bigger than the right end. And then you cover like the joint intervals. So you take the k intervals. And so what you want to do using this distribution result is you want to place your function tau in this interval. Placement, you want to sum that up over all these intervals I1, Ik, choosing them without losing Gaussian mass of these intervals, because you want to get these optimal exponents. And the observation here is very simple, that this problem of gluing the intervals, it naturally breaks down into two. So if I want to find the arrangement such that tau of n is strictly smaller, and so on and so forth, then it can only happen if, so what happens is that up to some point, you get that your tau function is smaller than 0, maybe empty set. And then after some other point, this tau function is actually bigger than 0. But then these two problems are completely independent, problem of smaller, we don't need to compare the order of magnitude. But whenever you have the smaller than 0 chain, then you must have the absolute values to be arranged in this way. I should put here the absolute value. And values have to be arranged in the, okay, there is a typo here. That should be less and less. That should be less, an absolute value. So the point is that these are completely disjoint problems. I can work on the set of negative and positive values and then sum up all these probabilities using our joint distribution result. And again, you need to be careful how you cover it because you don't want to lose anything in density. So you need to do some kind of optimal covering argument. Okay, so I'm not sure how much time I have, but I conclude here and saying that really, so I didn't go into the details, but really this is rather general phenomena of treating the questions of the following type. So I start off with the function multiplicative, and so I decompose this into, so I've got a e to the h, so h is an additive function, so it's for which I can prove Chola type result. So in my case, it was sine of tau. So whatever I described before, for many additive functions h, you can indeed prove this independence, joint Gaussian independence. And for many functions of g, you can prove some kind of form of a logarithmic Chola and so on and so forth. And so you could ask the same questions and treat other functions in this way. I guess I'll stop here. Thank you very much. I think this is, I used my 50 minutes.
I have a question.
Yes.
I'm a little confused because you seem to claim this lower bounds of a half and a sixth for the natural density, but used tau and Teravainen with the logarithmic density. What have you proved?
No. So I claim the upper density.
Oh,
and here I did use the upper density. So I could have stated these results with densities, but with logarithmic ones.
Oh, you tricked me because the second limb sup's got the line above, not.
Yeah. I know, because when I put the limb sup, it goes away. 1/6 you can't see.
Okay. So really you're saying logarithmic density, and as a corollary, you get this.
Exactly.
So I have one point to make, which is you do a strange thing here, which is that the result of on symmetric powers tells you that the sum of the nth moments of a lambda m, so take the sum of a lambda jp's to the m, that's little o of pi x. That's essentially what knowing about the L function is. So you really have a distribution. We know the distribution for the lambda jp's, not the logarithm of them. Then you take this result of Jesse's and then you convert it, and then you work with moments of the logarithm. So I'm just wondering whether you might get more by working directly with the original results on moments of what happens at the primes rather than Thorner's corollary.
Right. So the Turners, you also needed to show, because you need to show that your tau is actually, well, you need something about the science, but you do need to show that you are far from the characters, not only in the application of Erdős-Kac, but rather in the applications for the science as well, right? So, but for the distribution results, I guess, right. I don't really know, but
I don't know how it would be particularly useful in exactly what you've done, but
right. So okay.
So much more precise result than you're using.
So for the point is that for computing the moments, I don't really, I'm thinking right now that, you see, for the consequences, there is not really a loss. I don't know what exactly how I can do better in the sense of, so what you're saying that I would not need to treat the signs, right? That's what you're.
I don't know what I'm saying really. I mean, all I know is that, you know, directly from the Newton-Thorne result, you probably get the sum of lambda p's to the m is less than pi x over a large power of log or something like that, or even e to the minus root log. Right. And then the question is, what Thorne has to do is go from these moments and uniformity issues to distribution function, right? So it's just this classic thing that the moments tell you the probability distribution, but how well can you get the error terms? And I mean, the improvement over Taylor is that these new forms live over the rationals, so there's no base change, so it can all work. Anyway, that's irrelevant. The point is, it does work, and you can get pretty decent error terms as a corollary, I'm sure. But then you can presumably translate that into better error terms than you've got at the moment, because you're not, you know, Jesse was doing a calculation that you don't need to do.
Right, right. Oh, so you're saying, that's right. So, okay, I see what you were saying. Right. Okay, yeah, maybe this is a good point. Really, to adjust this to, so we really can use it, of course, as a black box, except that you need some information about progressions there, and indeed, perhaps that might.
Oh, I was going to ask that. So you said something about that. So you can, Thorner's result also allows you mod Q for Q fixed or something?
Even you can let Q to actually, well, Turner machinery, it's not the result, but really this machinery of approximation, you can let Q to even to grow to some powers of logs, like very cheaply.
So he's going to have to work for twists of these F.
Yeah. For that kind of.
Okay, and that all works, does it?
Yeah, it all works, and that's useful when you want to estimate the distances.
Okay, I just worry about the square free condition.
Oh yeah, so but the square free condition really goes like to that's what is in the work of Thorne and Newton.
Now what I'm saying is you start for new form F, and you twist it with a Dirichlet character. Maybe now you no longer have a square free conductor.
Okay, I would need to think about that.
I mean, this is a technical issue, but it probably needs resolving.
No, I think like the square freeness should not really be affected here in the sense of the wait.
Usually when you twist something, you do change the conductor.
Right. So okay, I think like the way really one can actually do, because Q is fixed here, then really what you need to do, you actually could probably get the bounds on the distance easily for Q fixed even without using without.
Okay.
But if you need Q to be growing, right, so I guess you could go for the distance. You could also use the Fourier results where they actually estimate the. Oh, you need some error terms as well. Okay, I would need to think about that a little bit.
My final comment is it's Lamer.
Oh, Lamer.
Not some Eastern European name.
Yeah, Lamer.
They're Russian, I guess, family, but they took an American pronunciation of a name.
Yeah, I guess for the distance, you could also do.
I have a question as well, but sorry. It's very noisy around here. Let me wait for a while. If anyone wants to ask something now, should go. Maybe now is a good moment. My question is about how dependent is your result on how you, which normalization of the coefficients you choose. I mean, you can choose the normal one, like, or you could use the analytic normalization, which is supposed that all between -2 and 2.
Right. So it's not very dependent in the sense of so if you're trying to do arrangements. So the key thing here is that when you normalize by n to some powers, really, then you n plus shifts are pretty much roughly of the same size. So they are actually smaller. The fluctuations in your normalization should be smaller than the normal fluctuation during Gaussian distribution of log lambda n. So this is the only thing what you need to have. So of course you could have done the same results for lambda of n divided by n to the 11 halves. You could have done these results like for different fluctuations, as long as you do not exceed the whatever you get from the central limit theorem. However, you need to, if you want to get this densities, one sharp densities, 1 over k factorials and 1 over k's, then you need to be careful there a little bit with the normalization, because if you don't want to lose anything, not just the positive density, then you have to be careful that you do not lose this Gaussian mass. But in general, it's not very it's not very dependent, really.
Thank you.
Hi, I'm just curious how to ask questions if the coefficient of the cusp form are a complex value. Can you formulate something similar? Or?
Right. So definitely the result about the absolute values of the coefficients, right? That really has nothing to do with integrality. So you could ask the same question with the absolute value, except instead of the sign version. So that would be one way to formulate, and then nothing would change. Now, if the question of for the complex value, if I give you, say, lambda of n plus 2, lambda of n plus 1, and lambda of n plus 2. So what you might do is, I guess you might take a circle. You might choose the orientation, and you, instead of the sign pattern or instead of the arrangement, you can, if you choose the orientation, you can say, okay, lambda n plus 1 is in between lambda of n and lambda of n plus 2. So that would be the analog of sign pattern, or the analog of the arrangement. That would be another way to do it, and I don't really know how to do it for even for just multiplicative functions, I guess.
So are you doing anything for elliptic curve L functions? Because essentially that's the same question, right? You're taking the real part to get your APs.
That's right. So, right, but I mean, so I guess the question was like about the arrangement. So there is no restriction there with the...
No, but if you think about moving along the curve, it's roughly the same thing as saying ordering the real parts.
Right.
And ordering the real parts is what you want to do if you're asking about the AN coefficients for the coefficients of an L function of elliptic curve.
Right.
So if you could do that, then maybe you can answer this question the way you like your interest. This will be the generic example, I guess, is the elliptic curve idea question.
Right. So that would be another way to put it. So okay. So I don't know how to do them, but that would be another question. So the question of arrangements, I can tell you that when the question of arrangements of these guys on the unit circle for complex valued functions, in general for complex valued multiplicative functions, it seemed to be hard. And here, yes, so for the real parts, indeed, arrangement.
Actually, I think that should be doable. I mean,
Maybe it's doable.
Auto-Tate is going to tell you that the primes are, you know the angle distribution pretty well. So now you're basically trying to do some sort of distribution inside.
Yeah, but so what exactly? So you want to arrange them into? So you want to have the sign, the chains of inequalities there also for the shifted coefficients, right? That's what you want to do.
I think that was what the question was. I think it's a good question. But I'm just saying that if you're just looking at the angles, which is what you're proposing, I mean, either you can look at the real part, which is almost the same.
It's the same thing.
Or you can just look at the distribution of angles. But Auto-Tate says on the primes there, we know what the distribution is. It's this Auto-Tate distribution. So, you know, it's probably accurate enough with Fourier's theorem to go from there.
Right.
You just have to divide. You have to do mod 2 pi.
Yeah, divide modulo. Yeah. Yeah, maybe. That's a good point. That's a good point. Yeah.
Actually, I think it's quite simple because you just take the 100 largest prime factors and they're going to be so randomly distributed. You're just in convolution started 100 times, which is uniform distribution. Mm-hmm. And then you can just tensor, you know, then it doesn't matter what all but the first 100 prime factors did. The last 100 will be uniformly distributed.
Yeah.
So I'm just thinking of Fn and how that distributes, or argument Fn, but your techniques essentially use the one-dimensional techniques. I mean,
mm-hmm.
Anyway, there's a chance.
Thank you. Yeah, I think you're right, probably indeed, because you can take just a couple of large primes and create a random behavior there already. Yeah, perhaps that's a good way to explore.
Okay, do we have more questions? I think that there are some questions in the chat.
Okay, so this is one, how to formulate similar question on sign change. Right, so this is the one that we just discussed. Real valued, yeah. So how I think we've discussed these questions right now, and that's the question that's been. Yeah. So I think everything has been discussed, like whatever was in the chat already.
Okay. Okay. Thank you very much, Oleksiy. Nice talk.
Very nice talk. Thank you, Oleksiy.
Thank you, Alex.
Thank you for the comments, questions.
And thank you everyone for coming.